Okay, so we are back for day 2 of chi-squared tests for goodness of fit. Remember, these tests are helping us check whether or not a claimed distribution for a categorical variable is correct or is accurate. All right, and yesterday we talked about an M&M example where we were assessing the claimed distribution of M&M colors for any M&M product. And remember, the very first thing we did was fill out that big table, which sort of helped us in an organized way calculate our test statistic, which ended up being 3.0755. Now that test statistic is what we found when we added up, we took the sum of all observed values from your sample minus the expected values, like the values you would guess you would see or expect to get in your sample based on the claimed percentages, divided by the expected values again, right? And that is on your formula sheet. It appears, shoot guys, I'm looking for your formula sheet. Right here is our formula sheet. And it is not loading. Here we go. Right here. So remember, chi-squared is like x squared is equal to the sum of all observed minus expected squared sums for every value or category divided by the expected. So that's at the very bottom of the front page of your formula sheet. And so we are going to practice doing this for a few different examples today. And then we're going to talk about the p-value. So this first one is that roulette example where we've got 38 slots, 18 that are red, 18 that are black, and 2 that are green. And it says, in one casino, managers record data from a random sample of 200 spins, like we said yesterday, noting the color spun each time. They use this data to run a chi-squared test for goodness of fit, and now we're going to find our chi-squared statistic. So if I'm given my data in a table like this, remember they thought we would have, out of our sample, we would have 18 of our 38 be red, 18 of the 38 be black, and 2 of the 38 be green. So our expected counts would be 18 of the 38. We did this yesterday times 20, or not 20, 200 spins. So we would expect to see 94.73. It's not really equal, I guess. It's just tells us the breakdown. 7.4 really, if we round up. For both of these, 94.74. And then 2 out of the 38 would be green times the sample of 200 spins, so 10.53 were going to be green. Now remember, we calculated those because they helped us check off our large counts condition. Remember, that says that all expected counts have to be at least 5, in which case, or in this case, they are. So now I'm going to find my chi-squared test statistic by doing the observed value. So for red, that's 85, minus the expected 94.74 squared over the expected value 94.74. And I'm going to add that to the next one, 99 observed black minus the 94.74 expected squared over 94.74. And then my last category, green, I observed 16. I expected 10.53 over 10.53. All right. So that is the pattern that we use. Then we calculate. So unfortunately, yes, you just have to plug them in. So I'll do 85 minus 94.74 squared divided by 94.74. Then on my calculator, I hit enter to find out that category's part of the test statistic. Then I hit plus and then do the next one. So Now we have 99 minus 94.74 squared over 94.74. All right. Plus 16 minus 10.53 squared over 10.53. Okay. And so I end up getting a test statistic of 4.0344. All right. And notice that some of these actual observed values are kind of far from the expected values. Like 85 is pretty far from 94. But then 99 and 94 are a little closer together. So remember, we are checking to see, are the actual values we observed quite different than the claimed values? And if so, then that might be evidence that the alternate hypothesis is the way to go. Now remember, to make that final conclusion, we get a p-value. And so let's just talk a little bit about chi-square distributions in general. They are a special type of distribution. They do not have symmetric curves like our normal curves and our t-curves. They are skewed. They take on only positive values. And every particular chi-square distribution is characterized by its number of degrees of freedom. And so in the goodness of fit test, we use a chi-square distribution with the degrees of freedom equal to the number of categories minus 1. All right, and so then the p-value ends up being the area to the right of the test statistic. So let's say our chi-square value was 4.03. In this case, our degrees of freedom would be 2 because it's 1 less than our number of categories. We had 3 colors. And so we don't have a degree of freedom equaling 2 curve, but let's just say it was this 4 one. Well, then our test statistic would fall about here. Our p-value would be that area all the way to the right. Okay, and so let's talk about how we find it. We are going to use chi-squared CDF in our second VARS menu. So just like we go to normal CDF and inverse norm, in our variables menu, second VARS, we're going to use our chi-squared CDF in that same menu. So now we're jumping back to our M&M example from yesterday. I'm going to pull up my notes from that day. Right here we have 1, 2, 3, 4, 5, 6 colors. So we would have 6 minus 1, so 5 degrees of freedom. And then we would use chi-squared CDF to find our test statistic. Now if you hit chi-squared CDF in that second VARS menu, it is number 8. And it asks for a variety of things. It says lower, upper, and degrees of freedom. Okay, the lower would be your test statistic always. All right, which we noted up here at the top for us was 3.0755. Then remember we shade all the way to the right, so up to 1,000 or 10,000 with 5 degrees of freedom. All right, and so if I punch that in my calculator, I've got 3.0755 to 1,000 with 5 degrees of freedom. And I get a p-value of 0.6883. Now, remembering what we know about tests of significance, that is a large p-value, right? You will never set a level of significance that will be lower than that p-value. And so in this case, we probably will end up failing to reject or getting an inconclusive test. All right, now we're going to do it for the casino example we did above. Remember here we said our degrees of freedom were equal to 2 because we had 3 color categories on the roulette wheel. And then we would say chi-squared CDF from our test statistic, 4.0344, all the way to 1,000 with 2 degrees of freedom. And so 4.0344 to 1,000. Oops. 2 degrees of freedom. We get a p-value of 0.133, which is also, well, 13302. So yeah, 133. Also kind of high, right? So on both of these cases, we're starting to see we maybe don't have enough evidence to disprove the claimed distribution that is given. So that's just sort of, I'm previewing something that we will see in the coming days or even tomorrow. But that is how we would do those examples. So now we're going to put it together and do the example that we talked about yesterday. So Malcolm Gladwell, his book, which discussed the idea that birth months are not equally represented by NHL hockey players. Remember, he took a random sample of 80 NHL players from a recent season, and here he's got a breakdown. Now notice we've got 3 months, January, February, March, then April, May, and June, then July, August, September, October, November, and December. So we would expect to see a quarter of our sample represented in each of those if each month was equally represented, right? And so here our expected counts would be 1/4 of 80. So 20 in this category, 20 in this category, 20 here, and 20 here. Right? So far we're seeing, holy cow, there's a lot born from January to March compared to the others. And that one has a lot larger observed value than its expected value. Okay. Now, if we had them broken down by each month, we do 1/12 of our 80 sample, right? And so that would mean we'd have 1/12 of the sample in January, 1/12 in February, 1/12 in March. So it kind of depends on how your data is broken down. Remember, in this one, we're checking to see is each category equally represented. So now our chi-squared statistic is equal to the observed, remember we're using our formula from up here, observed minus expected squared. So observed 32 minus expected 20 squared over the expected, plus observed minus 20 over 20, that's a lot of 20s. Then 16 minus 20 squared over 20, and then 12 minus 20 squared over 20. All right, so now I'm going to do a little calculator work. So 32 minus 20. Sometimes I shorten that and say, well, I know that's 12 squared over 20 plus, the next one's 0 because 20 minus 20, that's 0. And then the next one will be -4 squared sorry, I'm having a calculator issue, divided by 4 squared divided by 20. And then the next one will be 12 minus 20, so -8 squared divided by 20. And I end up getting 11.2, even, 11.2. Now the p-value for this, first we need our degrees of freedom. There are 4 categories here, so we have 3 degrees of freedom. So we would say chi-squared CDF from 11.2 all the way to the right to 1,000 with 3 degrees of freedom. So I go to second vars, chi-squared CDF, 11.2. And I get 0.0107. That's a small p-value, right? And so in this case, we would probably be able to reject the null hypothesis in favor of the alternate, right? Now that's where we're going to land tomorrow, is making those final conclusions. But we've got a pretty darn good start with our conditions, our hypotheses, our test statistic, and our p-value. All right, see what you can do on the practice, and we'll see you tomorrow.